Okay, are you ready to dive deep into some seriously cool fluid dynamics today?
I am.
We're tackling a paper that, really shakes up how we think about those equations. You
Yeah,
know,
right.
the ones that govern how fluids move. The Navier-Stokes and MHD equation.
Yes, exactly.
So this paper, it's by Cheskidov, Zhang, and Zhang, and they look at these things called dissipative solutions,
Right.
where the energy of the system is, steadily decreasing.
Yeah.
But here's the crazy part.
Yeah.
They proved that there can be infinitely many of these solutions, even if you start with the exact same initial conditions.
Yeah, it's a pretty remarkable result.
It's kind of like saying that, I don't know, a river can have countless different paths to the ocean,
Right, yeah.
starting from the same source. So why does this matter? We're talking some really complex math here.
Yeah.
So why should anyone besides mathematicians care about these dissipative solutions?
Because it really highlights how unpredictable even seemingly simple fluid systems can be. Think about it. We use the Navier-Stokes and MHD equations to model, everything from the weather to the movement of stars.
Oh, wow.
But if there can be infinitely many solutions, even with the same starting point, it means that our ability to predict those systems, is inherently limited.
Okay, so goodbye to perfect weather forecasts.
Yeah,
Right?
basically.
But are there any positive applications of this knowledge?
Absolutely. Think about modeling turbulence, for example. Turbulence is notoriously complex.
Yeah.
But this deeper understanding of dissipative solutions could lead to new and more accurate models.
Okay.
And this could have huge implications for fields like aeronautical engineering, weather prediction, and even astrophysics.
Okay, so even though we're dealing with abstract mathematics,
Yeah.
there are real-world implications down the line.
Definitely.
That's reassuring.
Yeah, for sure. The potential is vast.
So before we get into the nitty-gritty, let's make sure we're all on the same page.
Okay.
Let's start with the Navier-Stokes equations.
Yeah.
How would you sum those up for someone who maybe hasn't thought about them since college physics?
Well, imagine you have a fluid like water or air, and you want to describe how it moves and changes over time. The Navier-Stokes equations are a set of partial differential equations that do precisely that. They account for things like the fluid's velocity, pressure, viscosity, how resistant it is to flow, and the forces acting upon it.
Okay, so it's basically a mathematical model for how fluids flow.
Exactly.
And these equations have been around for a while, haven't they?
Since the 19th century.
Wow.
And they're notoriously difficult to solve in their full three-dimensional glory.
Yeah, that's what I've heard, which is where things start to get really interesting, right?
Right.
Because this paper focuses on a particular type of solution called Loray-Hoff solutions.
Exactly.
Can you tell us more about those?
Yeah, so Loray-Hoff solutions are a clash of weak solutions to the Navier-Stokes equations. And the weak part is crucial because it allows for solutions that might not be perfectly smooth or differentiable everywhere.
Okay.
They might have some irregularities, but they still capture the essential behavior of the fluid.
Okay, irregularities, got it. But what makes them so special in this context?
Well, for a long time, mathematicians have been trying to figure out if there even exist Loray-Hoff solutions where the energy strictly decreases over time. These are those dissipative solutions we've been talking about.
Right.
And this paper definitively answers that question.
Definitively meaning?
Meaning they found them.
Oh, wow.
Cheskidov, Zhang, and Zhang not only prove the existence of dissipative Loray-Hoff solutions, but also show that there are infinitely many of them, even when you start with smooth initial conditions.
Whoa, infinitely many solutions, all with decreasing energy. That's a lot to wrap our heads around. Yeah. So how did they actually pull this off? What kind of mathematical wizardry did they use to find these solutions?
They used a technique called convex integration. It's a powerful method for constructing solutions to partial differential equations, and it involves carefully piecing together specially designed functions, kind of like building with mathematical Legos, to create solutions that meet specific criteria.
So they're not just proving that these solutions exist in theory, they're actually building them step by step.
Exactly. And the way they leverage the dissipative term in the equations to achieve this is truly innovative. It's a different approach from earlier convex integration methods.
Okay, you've piqued our curiosity. Let's start piecing together this mathematical puzzle.
Okay.
How do they introduce this convex integration scheme?
Well, they begin by explaining their telescoping convex integration scheme. This scheme relies on building a sequence of solutions to a relaxed version of the MHD equations, which they call the MHD Reynolds system.
Hold on, the MHD Reynolds system. It's like a modified version of the regular MHD equations.
You got it. Think of it as a way to introduce a bit more flexibility into the equations, allowing for solutions that might not perfectly satisfy the original MHD equations, but get closer and closer with each iteration.
Okay, I'm starting to see the telescoping part.
Right.
They're creating a series of solutions that get progressively closer to the true dissipative solutions they're after.
Exactly.
Like honing in on it.
Yeah. And a key feature of this relaxed system is the inclusion of a term called the Reynolds stress,
Okay.
which helps them control the energy of the solution at each step.
I like that analogy. A pressure valve for mathematical energy.
Yeah, exactly.
So what are the key ingredients of this MHD Reynolds system?
Let's take a look at the equations themselves. They define the relaxed MHD Reynolds system for each integer in math.BBN as follows. Partial BQ, delta BQ plus DQ plus nabla BQ, partial BQ plus devQ cube BQ plus nabla BQ plus divu or tet BQ this PQ plus devQ plus BQ0N, BQ0N WQ or BQ0A or IIR A or H case.
Okay. Can we break those equations down a bit? What do all those symbols represent?
Of course. So UQ represents the velocity field at the qth step of the iteration, and BQ is the magnetic field at that step, and are the viscosity and resistivity coefficients, respectively, which describe how resistant the fluid is to flow and how easily electric currents can flow through it. PQ is the pressure, and V0 and H0 are the initial velocity and magnetic fields, respectively.
And what about those math-ring terms?
Yeah.
Those are the famous Reynolds stresses.
You got it. Math-ring represents the Reynolds stress for the velocity field, which is a symmetric traceless 3x3 matrix. And math-ring BQ is the magnetic stress, a skew-symmetric 3x3 matrix.
Okay, so these stresses are kind of like adjustments they're making to the original MHD equations at each step.
Exactly. And these adjustments allow them to fine-tune the energy behavior of the solution.
Now, I'm curious about those subscripts, the Q.
Yeah.
They're indicating that we're dealing with like a sequence of solutions, right?
That's right. The idea is to start with an initial approximation, U is 0, B0, and then iteratively construct a sequence of solutions, U1, B1, UB2, and so on, that get closer and closer to the true dissipative solution of the original MHD equations.
So how do they actually go about choosing these initial approximations? It can't just be random, right?
You're absolutely right. They need a starting point that's already reasonably well behaved.
Okay.
And that's where the concept of the MHD system comes in.
Okay, now we're getting into some new terminology. What is this lambda MHD system?
Yeah.
And how does it relate to the MHD Reynolds system?
Think of the lambda MHD system as a carefully smoothed out version of the original MHD equations. They choose a special wave number that basically acts as a high-frequency filter.
Okay.
This filter only allows low-frequency modes of the velocity and magnetic fields to interact, while the high-frequency modes are simply dissipated away.
So it's like they're taking out the really jumpy, chaotic parts of the solution and just focusing on the smoother, more manageable aspects.
That's a great way to put it. And this smoothing allows them to create an initial approximation that's both smooth and has a nicely decreasing energy profile, which is essential for their construction.
I can see how that would be like a helpful starting point.
Right.
But how do they actually ensure that the energy keeps decreasing as they iterate through this sequence of solutions?
That's where the magic of the telescoping energy levels comes in. They carefully select a sequence of decreasing energy targets, denoted by Q, that they want their approximate solutions to hit at specific times. It's like setting a series of checkpoints on a downhill race, making sure the energy racer keeps moving in the right direction.
Okay, so they have these energy checkpoints, but how do they guarantee that their solutions actually, reach those targets? That seems tricky.
It is.
Yeah.
And it requires a lot of careful mathematical maneuvering. But the essence of the idea is to design the Reynolds stresses in a way that forces the energy to decrease at the desired rate. It's like adding little energy bumps to the track at just the right places to guide the racer downhill.
I love these analogies. It really helps to visualize these abstract mathematical concepts.
Visualizing it definitely makes it more intuitive.
Yeah.
And that's what makes their approach so elegant. They combine a clear understanding of the underlying physics with clever mathematical techniques to create solutions that wouldn't have been possible to find otherwise.
Now, I know you mentioned that they use this technique for both the Navier-Stokes and MHD equations.
Right.
Are there any significant differences in how they apply it to each case?
That's a great question, and yes, there are some crucial distinctions. When it comes to the MHD equations, the presence of the magnetic field adds a whole new layer of complexity.
Of course. The magnetic field interacts with the fluid, creating additional forces and influences. How do they account for that in their construction?
They have to design new and more intricate building blocks, those mathematical Lego pieces we talked about, to capture the unique geometry of the MHD system.
Okay.
These building blocks are designed to not only control the fluid's velocity, but also to manipulate the magnetic field in just the right way.
So it's like they're playing with a more sophisticated set of Legos now.
Right. Exactly.
And I'm guessing the process of fitting these pieces together gets even more challenging.
It definitely does. But the underlying principle remains the same. They carefully choose these building blocks and arrange them in a way that ensures the energy of the solution keeps decreasing while simultaneously satisfying the MHD equations.
It's like a delicate balancing act. They're juggling these complex equations and energy constraints all at once.
It's truly impressive, the level of precision and ingenuity they bring to this problem.
So they've set up the overall scheme, they have their initial approximation from the lambda MHD system, and they have their energy checkpoints. What's the next step in actually constructing these dissipative solutions?
Now it's time to delve into the specifics of the iterative process.
Okay.
Each step involves a series of meticulously crafted mathematical operations that take them closer to the desired solution. And a crucial aspect of this process is carefully accounting for and canceling out various errors that arise from the building blocks themselves.
Errors? What kind of errors?
Well, remember those mathematical Legos we discussed?
Yeah.
Sometimes when you fit them together, there can be tiny gaps or overlaps that don't quite perfectly align with the desired outcome.
Okay, so they have to sand down those rough edges to make sure the solution fits smoothly.
That's a fantastic analogy, and that's where techniques like heat correctors and mollification techniques come into play.
Those sound like some serious mathematical tools. What do they do, exactly?
Heat correctors, as the name suggests, utilize properties of the heat equation to smooth out some of those high-frequency errors.
Okay.
The heat equation naturally describes how heat spreads out over time, and by incorporating elements of it into their construction, they can dampen those unwanted oscillations.
Ah, so it's like applying a mathematical heat treatment to the solution to make it more pliable.
Exactly. And mollification techniques involve convolving the solution with special smoothing functions that blur out some of those sharp edges and irregularities.
So it's a bit like applying a Gaussian blur to a photo to make it less pixelated.
You're getting it.
Okay.
These techniques allow them to control the errors with incredible precision, ensuring that the final solution remains valid and truly dissipative.
Okay. So they're carefully building these solutions step by step, accounting for errors along the way.
Right.
What's the grand finale of this mathematical construction project?
The grand finale is the rigorous proof.
Okay.
They have to show, beyond a shadow of a doubt, that the sequence of solutions they've created actually converges to a true dissipative solution of the original MHD equations.
Right. That's where the rubber meets the road. They have to back up their claims with solid mathematical reasoning. How do they go about that?
Well, it involves a lot of intricate calculations and estimation, carefully controlling the size of those errors at each step to ensure that they don't blow up and derail the whole process.
It sounds like a delicate operation.
It is,
Yeah.
but they demonstrate incredible mastery of the mathematical tools, guiding the reader through each step of the proof with clarity and rigor.
So before we delve into the step-by-step proof, can you give us a high-level overview of how they structure their argument?
Yeah.
What are the main chapters in this mathematical story?
Excellent question. The paper lays out the proof in a very systematic manner.
Okay.
They start by focusing on the lambda MHD system, proving the existence and key properties of its solution.
Okay.
Then they dive into the heart of the convex integration scheme,
Yeah.
describing the construction of the velocity and magnetic flows.
Okay.
These flows are the essential ingredients for their mathematical Legos.
So they're creating these special functions that they'll then use to build their solutions.
Yeah, precisely. And they have to prove a lot of intricate estimates about these flows to ensure they have the right properties to create those dissipative solutions.
Properties like?
Well, for example, they need to be highly localized in space, meaning they only have a significant impact in a small region.
Okay.
This localization is crucial for controlling the energy of the solution and making sure those energy bumps are strategically placed.
Okay, so they're building these tightly controlled mathematical pulses.
Yeah.
What else?
They also need to be highly oscillatory in time, meaning they fluctuate rapidly.
Uh-huh.
This rapid oscillation helps to cancel out those pesky errors we talked about earlier, kind of like shaking a rug to smooth out any wrinkles.
So they're not just like static building blocks. They're dynamic and fluctuating almost like, I don't know, tiny waves.
That's a great way to picture it.
Huh.
And the specific form of these flows, how they're localized and oscillate, is carefully chosen to fit the geometry of the MHD system, ensuring they interact with the fluid and magnetic fields in just the right way.
It's amazing how they're able to tailor these functions so precisely to achieve their goals.
It really highlights the elegance and power of mathematical tools. And then once they have these carefully constructed flows, they move on to the next chapter of the proof, where they assemble those flows, carefully weighted and positioned, to create the velocity and magnetic field perturbations at each step of the iteration.
So they're finally putting those Legos together. And I'm guessing they have to be very meticulous about how they place each piece.
Absolutely. Each flow has a specific role to play in driving the energy down and ensuring that the solution satisfies the MHD equations.
Right.
They have to control not only the amplitudes, the strength of each flow, but also their phases, their relative positions in time to achieve the desired outcome.
It sounds like a highly choreographed mathematical dance.
That's a great way to describe it.
Okay.
And as they're assembling these perturbations, they have to carefully account for the errors that inevitably arise, utilizing those heat correctors and mollification techniques we discussed earlier.
Right, they're smoothing out those rough edges along the way.
Yeah.
And then once they have this beautifully crafted solution, they have to prove that it actually works.
Right.
How do they approach that final step?
They meticulously demonstrate that their constructed solution satisfies all the requirements for a dissipative solution.
Okay.
They prove that its energy is continuous and strictly decreasing, and they show that it satisfies the MHD equations in the weak sense.
Weak sense, what does that mean exactly?
It means that the solution might not be perfectly smooth or differentiable everywhere, but it still satisfies the equations when tested against appropriate test functions. It's a way of accommodating solution that might have some mild irregularities while still capturing the essential physics of the system.
Got it. So it's still a valid solution, even if it's not perfectly, like, textbook smooth.
That's right.
Huh.
And this weak formulation is often necessary when dealing with complex, nonlinear equations like the MHD equations.
Okay, so they've gone through this incredible process of constructing these dissipative solutions.
Right.
But remember, their big claim was that there are infinitely many of these solutions.
Right, yes.
How do they demonstrate that?
Well, the key lies in the flexibility of their construction.
Okay.
They show that they can tweak certain parameters in their scheme, things like the initial energy profile or the precise placement of those energy checkpoints,
Right.
to create a whole family of distinct solutions,
Right.
each one unique, but all satisfying those essential properties of being dissipative.
So it's like they have a master blueprint that they can modify to create endless variations on the same theme.
That's a great analogy.
Okay.
And this flexibility is what ultimately allows them to prove the existence of infinitely many dissipative solutions.
So are we ready to finally roll up our sleeves and dive into the step-by-step proof?
Let's do it.
Okay, starting with the lambda MHD system.
Right.
What are the key steps in proving the existence and properties of its solutions?
The paper lays out the proof of Theorem 2.3, which focuses on the lambda MHD system in a clear step-by-step fashion.
Okay.
The first step involves establishing the global existence of a solution using the classical Galerkin method.
The Galerkin method. Can you give us a quick refresher on what that is?
Certainly. The Galerkin method is a powerful technique for approximating solutions to partial differential equations.
Oh.
It involves projecting the equations onto a finite dimensional subspace, kind of like creating a simplified low-resolution version of the problem,
Okay.
and then solving the equations within that subspace.
So it's like creating a rough draft of the solution before filling in all the details.
That's a great way to think about it.
Yeah.
And the beauty of the Galerkin method is that under the right conditions, as you increase the dimension of the subspace, as you add more detail to your rough draft,
Yeah.
the approximate solutions converge to a true solution of the original equations.
So they use this Galerkin method to show that a solution to the lambda MHD system actually, like, exists. What's the next step?
Next, they establish crucial energy estimates for these Galerkin approximations. Remember that Energy inequality for Leray-Hawk solutions we talked about earlier.
Yes.
Well, they prove a similar energy inequality for the lambda MHD system.
Okay.
Showing that the energy of the Galerkin approximations is bounded and controlled.
Okay, so they're showing that their solutions don't just exist, they also behave in like a predictable way when it comes to energy.
Exactly.
What's next?
Now comes the fun part. They bootstrap.
Okay.
They use those initial energy estimates to derive even stronger bounds on the solution and its derivatives.
Bootstrapping. What does that mean in this context?
It's a technique where you use a weaker estimate to prove a stronger estimate, kind of like pulling yourself up by your bootstraps.
Right, okay.
In this case, they leverage their initial energy bounds to show that the solution is actually much smoother and more well-behaved than initially assumed.
So they're iteratively improving their understanding of the solution's properties.
Exactly. They start with some basic knowledge about the solution and then use that knowledge to derive more and more refined information.
Okay, so they've bootstrapped their way to some impressive estimates for the solution.
Right.
What's the final step in dealing with the lambda MHD system?
The final step involves carefully analyzing the behavior of the solution as the wave number cutoff approaches infinity.
Right, that high-frequency filter. So what happens when they remove the filter, letting all those high frequencies back in?
That's the crucial question.
Yeah.
And what they demonstrate is that as lambda goes to infinity, the solution of the lambda MHD system converges, in a precise mathematical sense, to a solution of the original MHD equations.
Ah, so their smoothed-out approximation is actually like a good representation of the true solution.
Exactly. And this convergence is essential because it allows them to use the properties of the lambda MHD system solution, which they've carefully established, to infer properties about the true MHD solution. It's like building a stable foundation upon which they can construct their more complex dissipative solutions.
Okay, so they've thoroughly dealt with the lambda MHD system.
Right.
Now, it's time to get into the meat of the convex integration scheme, right?
You got it.
Building those velocity and magnetic flows.
That's where we see the real artistry of their approach.
So how do they start? What are the fundamental building blocks of these flows?
They begin by introducing what they call intermittent building blocks, which are specifically designed to create localized, rapidly oscillating flows.
Okay.
These building blocks are based on carefully chosen functions that are highly concentrated in space and rapidly oscillate in time, just like those tiny waves we talked about earlier.
Okay, so they're setting up their palette of mathematical paints to create these flows.
Yeah.
What are the specific functions they use?
They use functions like fire parallel and fillers, which are all carefully chosen to have specific localization properties.
And what about those subscripts and tilde parallel?
Yeah.
What do those represent?
Those are parameters that control the spatial concentration of the building blocks, controls the concentration along a specific direction,
Okay.
while tilde control the concentration in the perpendicular directions.
So it's like adjusting the width and height of a brushstroke.
That's a perfect analogy.
Hmm.
They can fine-tune the shape and size of these building blocks to fit the specific geometry of the problem.
And then they combine these functions with some oscillatory terms, right?
Exactly. They introduce parameters like move and sigma, which control the frequency of temporal oscillations.
Okay.
Think of it like adjusting the speed at which you wiggle the brush.
Okay, so they're creating these dynamic, localized functions. How do they actually use them to build the velocity and magnetic flows?
Well, they define the velocity flows denoted by WK using a combination of these functions. For instance, for sigma n lambda K1, K1, and lambda are sets of wave vectors, they define PS alpha K, PS sigma n lambda K to X alpha K1 AW to PAS K1.
Whoa. Can we unpack that a bit?
Yeah.
What are all those KS and alphas doing there?
Of course. So each WK represents a velocity flow associated with a specific wave vector.
Okay.
And K2 terms are components of an orthonormal basis associated with the K. And the alpha terms are carefully chosen shifts that ensure the flows associated with different K values have disjoint support.
Disjoint support, what does that mean?
It means that the flows don't overlap in space.
Okay.
They're like separate localized pulses of fluid motion.
Okay, that makes sense. So each WK is like a little vortex or jet of fluid, like moving in a specific direction.
That's a great way to visualize it. And by carefully choosing the parameters, tilde and sigma, they can control the size, shape, and oscillation frequency of each of these flows.
And they do something similar for the magnetic flows, right?
Exactly. They define magnetic flows using a similar combination of functions, but with K2 instead of K1. PSI2, PSK n lambda plus a K n lambda plus sigma x, K n lambda.
So those magnetic flows are kind of like the magnetic counterparts to the velocity flows.
Precisely.
Okay.
They represent localized fluctuations in the magnetic field, just like the velocity flows represent fluctuations in the fluid's velocity.
Okay, so they've created these velocity and magnetic flows. Now, I'm guessing there's more to it than just, like, defining the flows themselves, right?
You're absolutely right.
Yeah.
They have to make sure that these flows satisfy certain properties that are essential for their convex integration scheme.
Okay.
One key property is incompressibility, which means that the flows don't compress or expand the fluid as they move.
Okay, that makes sense. You can't have fluid suddenly, like, appearing or disappearing out of nowhere.
Right.
How do they ensure that these flows are incompressible?
They introduce something called incompressible correctors, which are additional terms they add to the flows to enforce this property.
So it's like adding a little patch to each flow to make sure it, like, plays nicely with the fluid.
That's a great way to put it. They essentially add a curl term to each flow to make it divergence-free, which is a mathematical way of saying it's incompressible.
Okay.
For instance, for the velocity flows, they define fac sigma 2, vigma 2 curl.
Okay.
And then they add this alpha term to the original to ensure that the total flow is incompressible. They do something similar for the magnetic flows as well.
Okay, so they've carefully crafted these incompressible flows. What's the next step in this building process? Experts.
Now they need to determine the amplitudes of these flows, like the strength or intensity of each flow.
Right.
Which are crucial for controlling the energy behavior of the solution.
Okay. So how do they go about, like, choosing these amplitudes? It seems like it would require a delicate touch to balance all those, like, competing factors.
You're absolutely right. It's a delicate dance, and they use a clever approach that leverages information from the previous step of the iteration. Remember those Reynolds and magnetic stresses, the math ring terms?
Yes, those pressure valves that help adjust the energy.
Exactly. They use those stresses to guide their choice of amplitudes. For example, for the magnetic flows, they define the amplitude as AKBT x BX.
Okay, can we break down that equation a bit? What's rho B term?
Okay, of course. So rho B is a function they define that essentially measures the size of the magnetic stress.
Okay.
It's given by rho BTX 2 epsilon B1 LQ2 plus math ring BX, where epsilon B is a small parameter and LQ is a mollification parameter.
Mollification parameter. That sounds familiar. Is that related to those mollification techniques they use to smooth out the errors?
You're spot on. Controls the degree of smoothing applied to the magnetic stress.
Okay.
And that term is a smooth function carefully chosen to satisfy certain geometric properties related to the arrangement of the magnetic flows.
So it's like a special shape factor that helps them fit those flows together just right.
Precisely. And by combining this shape factor with the size of the magnetic stress, they create an amplitude function that perfectly balances the need to decrease the magnetic stress while keeping the overall energy under control.
It's amazing how much, like, thought and care goes into choosing these amplitudes. They're not just, like, picking random numbers.
Yeah.
They're using information from the previous step.
Right.
And carefully tailoring the amplitudes to achieve their goals.
It's a beautiful example of how they blend intuition about the physics with rigorous mathematical techniques.
Yeah.
And they use a similar approach to determine the amplitudes of the velocity flows as well, carefully considering the Reynolds stress and other factors.
Okay, so they've defined these intricate flows, and they've chosen the amplitudes. What's the next step in assembling the solution?
Now they introduce the concept of principal parts, which are essentially the main contributions to the velocity and magnetic field perturbations.
Okay, so they're identifying the heavy hitters in their construction.
Exactly. For example, the magnetic principal part of the velocity perturbation, denoted by WQ, is defined as sum carc sum key B.
Okay, so they're summing up the contributions from all the magnetic flows.
Right.
Each weighted by its corresponding amplitude. Makes sense.
And they do something similar for the magnetic principal part of the magnetic field perturbation, denoted by dq plus 1p.
Okay, so they've got their principal parts.
Right.
What do they do with them?
Well, these principal parts are the workhorses of their construction.
Okay.
They use them to drive the energy down and to counteract the effects of those pesky Reynolds and magnetic stresses.
Uh-huh.
But there's one more crucial ingredient they need to add to the mix.
Ooh. And what's that?
It's the helicity corrector.
Helicity correcting. Now, that's a term I haven't heard before.
Right.
What in the world is helicity, and why does it need correcting?
Helicity is a measure of the knottedness or twistedness of a vector field.
Oh, okay.
It's a fundamental concept in fluid dynamics, especially in the context of MHD,
Yeah.
where the magnetic field lines can get all tangled up like a garden hose.
So it's like measuring how tangled the garden hose is.
That's a great analogy.
Yeah.
And it turns out that helicity plays a crucial role in the energy dynamics of MHD systems. In particular, there's a quantity called cross-helicity,
Okay.
which measures the alignment between the velocity and magnetic fields.
So they're making sure the velocity and magnetic fields are like playing nicely with each other.
Exactly. And they do this by introducing the helicity corrector, denoted by WQ plus 1H, DQ plus 1H, WQ plus 1 quel, where gamma is a function that measures the helicity error at each step.
Okay, so they're adding this corrector term to like nudge the cross helicity in the right direction.
Precisely. It's like a little steering wheel they use to keep the solution on track and ensure the velocity and magnetic fields don't become too entangled.
Okay, so they have their principal parts and their helicity corrector. Are we ready to finally put all these pieces together and build a complete solution?
Almost. We're missing one last but very important ingredient, those incompressible correctors we discussed earlier.
Right. We need to make sure those flows stay divergence-free and don't create or destroy fluid.
Exactly. So for the velocity perturbation, they define the incompressible corrector, WQ plus 1C. So lambda plus lambda plus sumda ln tilde t plus lambda plus sumdo, where those WCK terms are those curl terms that ensure incompressibility, preventing any unrealistic fluid compression or expansion.
Okay. And they do something similar for the magnetic field perturbation, right?
Precisely.
Okay.
They define DQ plus 1C analogously, using the corresponding curl terms for the magnetic flows.
Okay, so we have all the ingredients now, the principal parts, the helicity corrector, and the incompressible correctors. How do they finally combine these to create the full velocity and magnetic field perturbations?
They simply add them all up. The velocity perturbation, WQ plus 1, is given by plus G plus 1 dog G plus 1 CT plus 1 G plus 1 G plus 1 G plus 1 G plus 1 H plus 1 2 plus 1 G plus 1 G plus 1 T plus 1 T plus 1 G plus 1 P plus U G plus 1 Q plus 1 T plus 1 G plus 1 T plus U plus 1 P plus 1 T plus 1 T plus 1 A plus 1 C WQ plus 1 C plus 1 T plus T plus Q plus 1 H.
Hold on, I'm seeing a new term there. WQ plus 1H. What are those?
Those are the heat correctors. Remember those mathematical heat treatments we talked about?
Yes, to smooth out the high-frequency errors.
Exactly.
Right.
Those WQ plus 1H and DQ plus 1 terms are carefully designed functions that utilize properties of the heat equation to dampen those errors and ensure that the solution stays on track,
Okay.
preventing those high-frequency oscillations from becoming too large.
Okay, that makes sense.
Yeah.
And those GQ plus 1 terms, those are the temporal cutoffs, right?
Yes.
To control when and where these perturbations are active.
You got it. G plus 1 is a smooth function that's equal to 1 in the time interval where they want to add perturbations,
Okay.
and smoothly transitions to 0 outside that interval.
It's like a dimmer switch for those mathematical flows, allowing them to precisely control when and where those perturbations are applied. So they've meticulously constructed these perturbations. What's the next step?
Now it's time to prove that these perturbations actually do what they're supposed to do. They have to show that these perturbations lead to a decrease in energy, that the solution remains within the desired bounds,
Right.
and that those pesky Reynolds and magnetic stresses are kept in check. And this involves a lot of intricate estimates and calculations.
It sounds like a mathematical marathon.
Yeah.
How do they even begin to tackle such a complex task?
They break it down into manageable steps, focusing on different aspects of the solution's behavior. One crucial aspect is analyzing the energy error introduced by the perturbations. They need to ensure that this error is small enough to not derail the overall decrease in energy they've carefully orchestrated.
So they're making sure those perturbations don't oversteer and accidentally increase the energy.
Exactly. They meticulously track the energy contributions from each component of the perturbation, the principal parts, the helicity corrector, the incompressible correctors, and the heat correctors,
Yeah.
making sure they all work together harmoniously to achieve the desired outcome.
I can only imagine the amount of detail and precision involved in these calculations.
It's truly impressive. They leverage a variety of mathematical tools and techniques, from delicate estimates of those intricate building blocks to clever applications of inequalities and identities, all aimed at proving that their solution stays on track.
It's like watching a master craftsman at work, carefully shaping and refining each element of the solution. What are some of the key techniques they use to control those errors and ensure the energy keeps decreasing?
Well, one crucial tool is the decorrelation lemma, which helps them estimate the interaction between different building blocks and ensure that those interactions don't lead to unexpected energy increases. It's like making sure that the different brush strokes in their mathematical painting don't accidentally blend together and create unwanted colors.
I love that analogy.
Yeah.
So they're carefully orchestrating those interactions to keep the energy flowing in the right direction.
Yeah.
What other tricks do they have up their sleeves?
They also cleverly exploit the properties of those heat correctors and mollification techniques to further dampen those high-frequency errors. It's like applying a final coat of varnish to their mathematical masterpiece to smooth out any remaining imperfections.
So they're really taking a multi-pronged approach to controlling those errors and ensuring the solution, stays well behaved.
Precisely. And it's this combination of careful construction and rigorous analysis that allows them to prove their remarkable results.
Okay. They've meticulously built these perturbations and shown that they lead to a decrease in energy. What's the next hurdle they need to clear?
Now it's time to tackle those Reynolds and magnetic stresses head-on. They have to demonstrate that these stresses also decrease at the desired rate as they iterate through the construction, acting as those pressure valves they designed them to be.
So they're showing that those pressure valves are actually doing their job, releasing energy as the solution evolves.
That's right.
Okay.
And this involves a careful decomposition of the stresses into different components and then analyzing the behavior of each component separately.
Okay, so they're breaking down those complex stresses
Yeah.
into more manageable pieces.
Exactly. And they use a variety of techniques to estimate the size and behavior of each component, including those powerful spatial intermittency estimates we discussed earlier,
Yeah.
which describe how localized those energy fluctuations are. These estimates help them ensure that the stresses remain small and localized, preventing them from overwhelming the solution and disrupting that delicate energy cascade.
It's like they're carefully disassembling a complex machine, understanding each part's role,
Right.
and then putting it back together in a way that works even better than before.
That's a fantastic analogy. And it's this combination of deep understanding and precise mathematical control that allows them to prove their results with such rigor.
So they've shown that the energy decreases and the stresses decrease. What's the final step in this mathematical marathon?
The grand finale is proving that the sequence of solutions they've constructed actually converges to a true dissipative solution of the original MHD equations. This is where they show that all their hard work pays off and that their intricate construction leads to a valid solution that captures the desired behavior.
Right. That's the moment of truth. They've done all this work, and now they have to show that it all, pays off. How do they approach this final challenge?
They demonstrate that the sequence of solutions forms a Cauchy sequence in an appropriate function space. This means that the solutions get closer and closer to each other as the iteration progresses, just like those runners bunching up at the finish line.
So it's like watching a series of blurry photographs gradually coming into focus.
Exactly. And this convergence property is essential because it guarantees that there's a well-defined limit to the sequence of solutions, the true dissipative solution they've been seeking.
And that limit is the dissipative solution they've been seeking all along, the solution that satisfies all those requirements and captures that elusive behavior of steadily decreasing energy.
Precisely. And they prove that this limit solution satisfies all the requirements. Its energy is continuous and strictly decreasing. It satisfies the MHD equations in the weak sense,
Right.
meaning it captures the essential physics, even if it has some mild irregularities.
Got it.
And it matches the prescribed initial data, starting at the same point as all those energy racers.
It's a triumphant conclusion to a truly impressive mathematical journey. They've meticulously constructed these dissipative solutions step by step,
Right.
carefully guiding those energy racers through those carefully crafted energy landscapes.
Right.
And they've rigorously proven that these solutions exist and satisfy all the desired properties.
Yeah.
Backing up their claims with, like, solid mathematical reasoning and showcasing their mastery of those powerful tools and techniques.
It's a testament to the power of human ingenuity and the beauty of mathematical reasoning, demonstrating that even in the face of such complex and challenging equations, we can still find elegant and insightful solutions, revealing those hidden truths about the universe and pushing the boundaries of our knowledge.
Well, I think we've covered a lot of ground here, from the intricate details of their construction to the broader implications for our understanding of fluid dynamics and its fundamental principles.
Yeah.
But before we move on, I think it's worth taking a moment to appreciate the mathematical tools and techniques they employ to achieve these remarkable results. Can you give us a sense of what makes their approach so elegant and powerful beyond those, like, clever analogies and conceptual explanations?
Absolutely.
Yeah.
Their work is a treasure trove of sophisticated mathematical tools and techniques, and it would be impossible to cover everything in detail here.
Right.
But let's highlight a few of the most elegant and insightful aspects of their approach,
Okay.
revealing the mathematical machinery behind their construction.
Okay. Lead the way. I'm ready to get my hands dirty with some math and see those equations in action.
Well, one standout feature is their masterful use of harmonic analysis,
Okay.
a branch of mathematics that deals with representing functions as sums of simpler oscillatory functions like sines and cosines.
Okay. So it's like breaking down a complex sound into its individual frequencies, revealing the hidden harmonies within a seemingly chaotic noise.
That's a fantastic analogy, and just like analyzing a sound's frequency spectrum can reveal hidden patterns.
Yeah.
Applying harmonic analysis to these fluid equations can uncover deep structures and relationships that would otherwise remain obscured.
So how do they actually use harmonic analysis in their construction?
Yeah.
How do they apply those sines and cosines to those, like, swirling flows and tangled magnetic fields?
They utilize Fourier transforms, a powerful tool in harmonic analysis, to represent their solutions in frequency space.
Okay.
This allows them to manipulate the different frequency components of the solution independently, which is crucial for controlling the energy behavior
Wow.
and those pesky errors we talked about earlier.
So it's like they're working with a mathematical equalizer,
Right.
boosting some frequencies and dampening others to create the desired outcome, shaping the energy landscape to guide those racers along the right paths.
Precisely. And this manipulation of frequencies is essential for ensuring that the energy cascades down to lower frequencies, leading to the dissipative behavior thereafter.
Okay.
It's like channeling the energy flow,
Yeah.
directing it from those chaotic high frequencies to the smoother, more stable low frequencies.
It's amazing how they can leverage these abstract mathematical tools to achieve such concrete physical results, shaping those swirling flows and tangled magnetic fields with the power of sines and cosines.
It really is remarkable.
Are there any other mathematical highlights that stand out to you? Any other tools or techniques that showcase their mathematical artistry?
Another impressive aspect is their use of sophisticated inequalities and embeddings.
Okay.
Inequalities are mathematical statements that compare the sizes of different quantities, acting as those mathematical measuring sticks we talked about earlier.
Right.
And embeddings are ways of relating different function spaces, sets of functions with certain properties, like mapping out the relationships between different neighborhoods in this mathematical city.
Okay, so it's like having a set of mathematical measuring tools to compare and relate different aspects of their solutions.
Yes.
Ensuring that everything, like, fits together harmoniously and stays within the desired bounds.
Exactly. And they use these tools with incredible skill to control the growth of various terms in their construction,
Okay.
preventing those errors from spiraling out of control and disrupting that delicate energy cascade.
So they have to be really careful with that.
It's like a master architect, ensuring that the weight of each beam and column is carefully balanced, preventing the entire structure from collapsing.
It sounds like a delicate balancing act. Carefully estimating and comparing different quantities to keep the solution on track.
Right.
What are some of those specific inequalities and embeddings they employ? Can you give us, like, a glimpse into their mathematical toolbox?
One family of inequalities they utilize are Sobolev inequalities,
Okay.
which relate the norms, measures of size, of functions, and their derivatives. These inequalities provide a crucial link between the size of a function and the smoothness of its variations.
Norms. Could you give us like a quick refresher on what those are? I remember those from calculus, but I'm a bit rusty on the details.
Of course. A norm is essentially a way of measuring the size or magnitude of a mathematical object. For a function, the norm might measure its maximum value,
Right.
its average value,
Okay.
or some other characteristic that captures its overall behavior.
Okay, so it's like having different ways of measuring the strength of a function.
Exactly. And Sobolev inequalities provide a crucial link between the size of a function and the size of its derivatives, allowing them to control how quickly those functions change and prevent those energy bumps from becoming too steep.
It's fascinating how they're able to connect these like seemingly abstract mathematical concepts to the physical properties of their solutions, bridging the gap between those equations and those swirling flows.
It is quite remarkable.
Are there any other specific inequalities or embeddings that play a key role in their work? Any other tools they use to like tame those unruly equations?
Yes. They also make clever use of interpolation inequalities, which are tools for estimating the size of a function in one function space based on its size in other function spaces.
Okay.
It's like figuring out the price of a car based on the prices of similar cars, using those comparisons to refine their understanding of those mathematical objects.
So they're using information from different mathematical markets to get like a better handle on the behavior of their solutions, leveraging those comparisons to make more precise estimates.
That's a great way to think about it.
Okay.
And they also utilize embeddings between different function spaces, such as the Sobolev embedding theorem, which allows them to relate the smoothness of a function to its integrability properties.
Okay.
How well behaved it is when integrated over a certain region.
Okay.
It's like understanding how the shape of a container influences how much liquid it can hold,
Right.
connecting those geometric properties to those analytical properties.
Okay, so they're weaving together a tapestry of mathematical tools and techniques, each one playing a specific role in controlling those errors and ensuring the solution converges to the desired outcome. It's like a symphony of mathematical concepts, all working in harmony to create this elegant and powerful result.
Precisely. It's this combination of deep mathematical understanding and creative problem solving that makes their work so impressive, showcasing the beauty and power of mathematics to tackle complex problems and reveal hidden truths about the natural world.
Now, I know we've talked a lot about the technical details of their construction, but I think it's important to step back for a moment and appreciate the broader significance of their work.
Right.
What are some of the key takeaways for someone who might not be like a mathematician, but is still fascinated by the mysteries of fluid dynamics?
Excellent point. Their work highlights the inherent complexity and beauty of fluid behavior,
Yeah.
even in seemingly simple systems. It reminds us that the natural world is full of surprises and that our understanding of it is constantly evolving.
Right.
What we thought was a single predictable path for those energy racers turns out to be a vast network of possibilities, all governed by those same fundamental laws.
It's a humbling reminder that there's always more to learn, always more to discover about the universe we inhabit, even in areas that we thought we had already, mapped out.
Absolutely. And it also underscores the power of mathematics to reveal hidden truths about the world around us. Their work is a testament to the creativity and ingenuity of mathematicians and their ability to unlock the secrets of nature, using those abstract symbols and equations to illuminate the hidden workings of those swirling flows and tangled magnetic fields.
I couldn't agree more. It's inspiring to see how abstract mathematical concepts can have such profound implications for our understanding of the physical world, connecting those elegant equations to the turbulent reality of our universe.
Okay, I think we've explored those technical details and broader implications sufficiently for now. Let's dive back into the heart of their construction and explore the step-by-step proof of their main result, revealing how they piece together those mathematical Legos and rigorously demonstrate the existence of those infinitely many dissipative solutions. Where do we begin this mathematical journey?
The journey begins with a crucial lemma, lemma 2.4 in the paper, which establishes the decay of the initial Reynolds and magnetic stresses. It's the foundation upon which they build their entire construction, ensuring that those pressure valves are well behaved and don't disrupt the delicate energy flow they're trying to create.
Okay, those pressure valves for the energy.
Yes.
Why is their decay so important? Why do those stresses need to, fade away for their construction to work.
Remember, the goal is to construct solutions where the energy is continuously decreasing.
Right.
Like those energy racers steadily descending those carefully designed slopes, and those stresses, if not carefully controlled, can act as sources of energy, potentially disrupting that decreasing trend and sending those racers off course.
So they need to ensure those stresses are like well behaved and don't inject too much energy into the system, like making sure those dams don't burst and flood the racetrack.
Exactly. Lemma 2.4 proves that the initial Reynolds and magnetic stresses, as defined in their construction, actually vanish as time approaches both 0 and t, a specific time point in their scheme.
Okay.
This vanishing property is essential for ensuring that the energy starts decreasing right from the beginning and continues to decrease smoothly throughout the entire time interval. It's like making sure that the racetrack starts at the highest point and gradually slopes downward, allowing those racers to maintain a steady descent without any sudden jolts or uphill climbs.
Okay, so they've tamed those stresses right from the start.
Right.
Ensuring that those energy racers have a smooth downhill path ahead of them. What's the next step in their construction?
Now it's time to set up the stage for their iterative process. They introduce two crucial sequences of time points. A backward sequence denoted by a forward sequence denoted by Thim. These sequences define the time intervals where they'll add those carefully crafted perturbations to the solution, those little wiggles that nudge those energy racers along their paths.
Backward and forward.
Yeah.
That sounds intriguing. What's the purpose of having these two sequences? Why not just have like one sequence that marches steadily through time?
These sequences define the time intervals where they'll add those carefully crafted perturbations to the solution.
Okay.
Those little wiggles that nudge those energy racers along their paths.
Okay.
The backward sequence marches backward in time,
Okay.
starting from a point close to t and approaching 0.
Okay.
And the forward sequence marches forward in time, starting from a point close to 0 and approaching t.
So it's like they're sandwiching the time interval between these two like converging sequences, gradually narrowing the gap and focusing their attention on the behavior of the solution as it approaches those endpoints.
That's a great way to picture it. And the reason for this backward-forward approach is to ensure that they have enough control over the solution's behavior as they approach both the initial time, 0, and that specific time point t. Remember, they need to guarantee that the energy is decreasing smoothly throughout the entire interval, and this approach allows them to carefully monitor the energy flow as it approaches those critical points.
Okay, I'm starting to see the strategy here.
Yeah.
They're carefully dividing the time interval into like smaller and smaller pieces, allowing them to fine-tune the solution's behavior at each step.
Right.
And ensure that those energy racers are always heading downhill, even as they approach those tricky starting and ending points. But how do they actually, like, choose these time points? What criteria do they use to determine where to place those checkpoints on the racetrack?
They choose the time points in a very specific way to ensure that the Reynolds and magnetic stresses remain small enough to not disrupt the energy decay.
Okay.
Remember, those stresses are like potential obstacles on the racetrack, and they need to make sure those obstacles are small enough that the racers can easily navigate them without getting thrown off course.
Okay.
For instance, they choose T1, such that the initial stresses are sufficiently small in the interval, giving those racers a smooth start to their descent.
So they're picking those time points strategically to keep those stresses in check, ensuring that those energy racers have a smooth and controlled descent.
Exactly.
What about the other time points? How do they continue this process and like refine those intervals as those sequences converge?
They proceed iteratively, building upon those previous choices to further refine the racetrack and ensure those energy racers stay on course. For each Q, they choose TQ plus 1, such that the stresses remain small in the intervals, 0 plus 1 and SQ plus 1T. They're essentially shrinking those intervals, making those checkpoints closer and closer together, while still maintaining that crucial control over those stresses.
Right.
And they also ensure that these intervals are nested within the previous intervals, meaning TQ plus 1, TQ plus 1 SQ, creating a series of ever-shrinking intervals, each one with controlled stresses.
So they're creating a series of ever-shrinking time intervals, each one with controlled stresses, like narrowing the focus of a microscope to examine those like finer details of the solution's behavior.
Exactly. And this careful choice of time points is crucial for the success of their construction, providing the framework for their iterative process,
Right.
and ensuring that those energy racers have a smooth and controlled path towards their destination.
Okay, they've set the stage with these time sequences, carefully laying out the racetrack and placing those checkpoints to keep those stresses in check. What's the next step in their iterative process? How do they actually start, like, building those solutions and guiding those energy racers along their designated paths?
Now comes the heart of the convex integration scheme, constructing the velocity and magnetic field perturbations at each step. Remember those intricate building blocks we talked about earlier?
Yes.
Those localized, rapidly oscillating functions?
Yes, those mathematical Legos they use to create the flows, carefully designed to, like, shape those energy bumps and guide those racers along their paths.
Precisely. At each step, they combine these building blocks, weighted by carefully chosen amplitudes, to create perturbations, WQ+1 and DQ+1, for the velocity and magnetic fields, respectively.
Okay.
These perturbations act as those little wiggles we talked about earlier, those subtle adjustments that nudge the solution in the right direction.
So they're adding these little wiggles to the solution at specific time intervals, guided by those time sequences they established earlier. But what's the purpose of these perturbations? What role do they play in, like, shaping those energy landscapes?
Shaping those energy landscapes and guiding those energy racers along their designated paths. Well, the goal of these perturbations is twofold. First, they need to counteract the effects of the Reynolds and magnetic stresses, those potential obstacles that could disrupt the energy decay and send those racers off course. It's like strategically placing those energy bumps to smooth out the track and ensure those racers maintain a steady descent.
So it's like they're applying counterforces to keep the energy, like, flowing in the right direction, carefully balancing those potential disruptions to create a more controlled and predictable path.
Exactly. And second, these perturbations need to drive the energy down towards those predefined energy targets, those checkpoints they established earlier to guide those energy racers toward their destination.
Right, those energy checkpoints they set up earlier, those milestones along the downhill path. Right.
So they're essentially nudging the solution towards those checkpoints with each perturbation, making sure those racers, like, hit those targets and maintain that steady energy descent.
Precisely. And the way they achieve this is incredibly clever. They carefully choose the amplitudes and phases of those building blocks, those mathematical Lego bricks, to create perturbations that simultaneously cancel out the stresses and guide the energy downward. It's like they're not just placing those energy bumps randomly, they're carefully shaping and positioning them to create, like, a smooth and efficient path for those racers.
It sounds like a delicate balancing act, requiring a deep understanding of those intricate equations.
It is.
And a keen eye for those subtle energy interactions. It is, and it requires a deep understanding of the interplay between the different terms in the equations and the properties of those building blocks. They have to carefully consider how those perturbations will interact with the velocity and magnetic fields, how they'll influence those stresses, and how they'll contribute to that overall energy cascade. But they demonstrate, like, remarkable mastery of these concepts, carefully orchestrating the perturbations to achieve the desired outcome, guiding those energy racers with remarkable precision.
Okay. They've created these perturbations, these carefully crafted adjustments to the solution, but how do they ensure that these perturbations don't introduce any new problems or instabilities? How do they make sure those energy bumps don't become, like, too steep or create unintended obstacles on the racetrack?
That's a crucial question, and it's where those heat correctors and modification techniques we discussed earlier play, like, a vital role. Remember, those techniques are designed to smooth out any rough edges and prevent those high-frequency oscillations from causing trouble, like sanding down those energy bumps and ensuring a smooth ride for those racers.
Right, those mathematical heat treatments and Gaussian blurs that, like, soften those sharp edges and prevent those energy fluctuations from spiraling out of control.
Exactly. They apply these techniques meticulously at each step, ensuring that the perturbations remain well-behaved and don't disrupt the overall structure of the solution. It's like carefully sanding and polishing each piece before fitting it into the puzzle, making sure everything fits together smoothly and seamlessly.
Okay, so they're carefully crafting these perturbations, smoothing out any rough edges, and ensuring they don't disrupt that delicate energy cascade. What's the next step in their iterative process? How do they incorporate those perturbations into the solution and, like, move towards that final convergent result?
Once they've constructed the perturbations for step, they update the velocity and magnetic fields, incorporating those carefully crafted adjustments into the solution. UQ+1, UQ plus WQ+1, and BQ+1 and BQ+1. It's like those energy racers have reached a checkpoint, received their instructions, and are now adjusting their course to head towards the next checkpoint.
So they're adding those perturbations to the previous solution to create the next solution in the sequence, gradually refining their path as they move towards that final destination.
Precisely. And then they have to prove like a whole set of intricate estimates to show that this new solution, UQ plus 1, BQ plus 1, satisfies all the desired properties. They need to demonstrate that its energy is decreasing, that those stresses are controlled, and that the solution remains within the specified bounds, ensuring that those energy racers are still heading downhill, haven't veered off course, and haven't exceeded any speed limits.
It sounds like a lot of work at each step.
It is.
They're not just like building those solutions. They're meticulously checking and rechecking every detail to make sure everything is still like working as intended.
It is, but they lay out the proof very clearly, carefully guiding the reader through each step and highlighting the key insights. It's not just about those like raw calculations, it's about understanding the motivation behind each step, the logic that drives their choices, and the subtle interplay between those different components of the solution. And it's in these details that the true beauty and power of their approach shine through, revealing the elegance and precision of their mathematical craftsmanship.
Okay. They've iterated through this process, creating the sequence of solutions that get closer and closer to their goal, those energy racers, steadily approaching that finish line.
Right.
What's the final step in their grand construction? How do they demonstrate that this iterative process actually leads to like a valid dissipative solution to those complex fluid equations?
The final step involves proving that this sequence of solutions actually converges to a true dissipative solution of the original MHD equations. This is where they show that all those carefully crafted perturbations, all those adjustments and refinements, actually lead to a solution that satisfies those essential properties of decreasing energy, adhering to the equations, and matching the initial conditions. They achieve this by demonstrating that the sequence forms a Cauchy sequence in an appropriate function space, showing that those solutions are getting closer and closer to each other as the iteration progresses.
A Cauchy sequence. Can you remind us what that is? It sounds familiar, but I need like a refresher on the details.
Certainly. A Cauchy sequence is a sequence where the terms get arbitrarily close to each other as the sequence progresses. It's like watching a group of runners bunching closer and closer together as they approach the finish line, their paths converging towards that common destination.
Okay, so the solutions are getting tighter and tighter as the iteration goes on. Like those energy racers all funneling towards that finish line, their paths becoming like indistinguishable.
Exactly. And this Cauchy property is essential because it guarantees that there's a well-defined limit to this sequence, a unique finish line that the solutions are converging towards. This limit isn't just some abstract concept, it's the true dissipative solution they've been seeking all along, the solution that emerges from this intricate and meticulously crafted construction.
And that limit is the dissipative solution they've been seeking all along, the solution that satisfies all those requirements and captures that elusive behavior of steadily decreasing energy.
Precisely. And they prove that this limit solution satisfies all the requirements. Its energy is continuous and strictly decreasing. It satisfies the MHD equations in a weak sense, meaning it captures the essential physics even if it has some mild irregularities, and it matches the prescribed initial data starting at the same point as all those energy racers.
It's a triumphant conclusion to a truly impressive mathematical journey. They've meticulously constructed these dissipative solutions step by step, carefully guiding those energy racers through those carefully crafted energy landscapes. And they've rigorously proven that these solutions exist and satisfy all the desired properties, backing up their claims with like solid mathematical reasoning and showcasing their mastery of those powerful tools and techniques.
It's a testament to the power of human ingenuity and the beauty of mathematical reasoning, demonstrating that even in the face of such complex and challenging equations, we can still find elegant and insightful solutions, revealing those hidden truths about the universe and pushing the boundaries of our knowledge.
Well, I think we've thoroughly explored the depths of this paper, from those initial energy landscapes to those intricate perturbations and those final convergent solutions. Any final thoughts before we wrap up this deep dive?
Their work is a powerful reminder that even in fields that we think we understand well, there are always new discoveries to be made, always new perspectives to be gained. The world of fluid dynamics, as revealed by this paper, is far more complex and nuanced than we might have imagined, with those seemingly simple equations giving rise to a vast and intricate landscape of possibilities.
It's a call to stay curious, keep asking questions, and never stop exploring the mysteries of the universe, both big and small. Who knows what other groundbreaking discoveries await us as we continue to push the boundaries of human knowledge and delve into the depths of those fascinating equations that govern the world around us.
Absolutely. And this paper serves as a beacon, guiding us towards those new frontiers and reminding us of the power of human ingenuity and the beauty of mathematical reasoning.
Well, thanks for joining us on this mathematical adventure. We'll see you next time on The Deep Dive, where we'll continue to explore the fascinating and ever-evolving world of science and mathematics. Okay, so today we're diving deep into some pretty complex fluid dynamics.
Yeah.
We're talking about the 3D Navier-Stokes and MHD equations.
Right.
The math behind how fluids and electrically conductive fluids like plasmas actually move.
Precisely. And the focus here is on a particular kind of solution called a dissipative solution.
Okay.
Buckle up. It's fascinating stuff.
I love how this paper reframes the problem.
Yeah.
We usually think of viscosity as something that smooths things out, right?
Right.
But here it's the key to unlocking a whole new world of solutions.
Exactly. And it challenges some long-held assumptions in the field.
Okay.
Let's start by discussing weak solutions to the Navier-Stokes equations.
Okay, so remind me what those are again.
Essentially, weak solutions are a way to make sense of solutions to equations like Navier-Stokes, even when those solutions aren't perfectly smooth.
Okay.
Think about a fluid with sudden changes or discontinuities in its flow.
Mm-hmm.
Weak solutions provide the mathematical framework to analyze these less-than-ideal scenarios.
Got it. So it's a way to handle the more turbulent aspects of fluid behavior where things aren't all smooth sailing.
Precisely. Now, a big open question in this area has been, can we mathematically guarantee that the energy of a fluid always decreases in these weak solutions?
Okay.
Physically, that makes sense, right?
Yeah.
Because viscosity should cause energy to dissipate.
Right. That makes sense. Like if you stir a
Yeah.
cup of coffee, eventually it settles down as the energy from your stirring dissipates.
Exactly. Now, this paper introduces the idea of dissipative solutions to the Navier-Stokes equations.
Okay.
These are special types of weak solutions where we can prove mathematically that the energy decreases continuously over time.
So it's not just an observation that energy dissipates.
Yeah.
They've mathematically nailed down that it must happen in these dissipative solutions.
Yeah.
That's pretty impressive.
It is, and it leads to a significant finding smooth solutions, where the fluid flow changes gradually aren't the only kinds of dissipative solutions that exist.
Okay.
There's a whole universe of non-unique solutions out there waiting to be explored.
That's where it gets really interesting, doesn't it?
Yeah.
And this paper doesn't stop at just Navier-Stokes.
Right.
They go even further into the realm of MHD equations.
Yes, and that's a major accomplishment.
Okay.
And the MHD equations add another layer of complexity by incorporating magnetic fields into the mix.
Mm-hmm.
Think about the swirling electrically charged plasmas found in stars. Those are governed by MHD.
So they found dissipative solutions for both Navier-Stokes and MHD equations.
Yes.
What are the implications of that finding?
It really expands the landscape of fluid dynamics.
Okay.
Imagine scenarios like the flow of liquid metals in industrial processes, or the dynamics of plasmas in fusion reactors.
Okay.
These dissipative solutions provide a more comprehensive framework to understand these complex phenomena.
It's like we've gone from having a standard roadmap to suddenly having a detailed atlas revealing all sorts of hidden paths and possibilities.
Yeah.
Now, I'm curious about the how
Right.
how did they manage to construct these dissipative solutions? The paper mentions something called a telescoping convex integration scheme.
That's the heart of their method, and it's quite ingenious.
All right.
Imagine building a complex structure like a tower from individual blocks.
Okay.
The telescoping scheme works by starting with an approximate solution and iteratively adding small, carefully designed perturbations.
Okay, so they're essentially refining their solution step by step using these perturbations as building blocks.
Exactly. And here's the brilliant part. They leverage the dissipative or viscous term in the equations to ensure that the energy decreases with each step.
Okay.
It's like using the natural tendency of the fluid to settle down as a guide to build their solution.
That's so clever. It's like using the fluid's inherent properties to control the construction process.
Precisely. Now, to dive a little deeper, let's talk about another key aspect of their approach.
Okay.
The lambda MHD system.
Okay.
This system introduces an approximation technique that's quite innovative.
Okay, I'm all ears.
Think about a fluid's motion as a combination of different frequencies. Just like sound waves have different pitches,
Right.
the lambda MHD system is designed to focus on the low-frequency modes of the fluid's motion while allowing the high-frequency ones to dissipate.
So it's like filtering out the noise of the high frequencies and concentrating on the more dominant lower frequency motions.
Yes, and this has a clever impact on the energy balance.
Okay.
By controlling which frequencies are amplified or dampened, they can finely tune the energy of their approximate solutions, ensuring that it decreases smoothly over time.
That's a pretty elegant way to manage the energy flow, isn't it?
It is.
To create these perturbations, they use specific building blocks called Barks flows.
Right.
These are fascinating because they're inspired by previous work in fluid dynamics.
Yeah.
What are these box flows and why are they important in this context?
Imagine tiny concentrated bursts of flow, almost like miniature jets occurring in specific regions of the fluid. That's what box flows resemble. They're designed to be highly localized and carefully placed to control the error terms that arise in the approximation process.
So they're strategically positioned to smooth out any wrinkles in the solution, so to speak.
Exactly, and it's important to note that building these box flows for MHD is much more challenging than for Navier-Stokes because you have to account for the interactions between the fluid flow and the magnetic field.
Right. It's like having to choreograph a dance between two different entities, making sure their movements are coordinated and contribute to the overall harmony.
I like that analogy.
To streamline their scheme further, they introduce a single heat corrector.
Okay.
Tell me more about this heat corrector. Why is it necessary?
The heat corrector is a brilliant way to manage errors that inevitably crop up during the iterative process.
Right.
Think about how heat naturally spreads out and dissipates over time. The heat corrector capitalizes on this principle.
So it's like using the heat equation's natural tendency to smooth things out as a way to cancel out errors that might accumulate.
Exactly, and it's closely connected to the concept of a pullback attractor, a mathematical concept that describes how solutions to certain equations, like the heat equation, tend to evolve towards a particular stable state over time.
Got it.
It's something worth exploring further if you're interested in the deeper mathematical underpinnings of this method.
That's a great tip. I always love a good rabbit hole to dive into. So let's talk about the results.
Sure.
The paper presents some rigorous mathematical theorems.
Right.
What are the key takeaways?
Their theorems formally establish the existence of infinitely many dissipative solutions for both the Navier-Stokes and MHD equations.
Wow.
This confirms that there's not just one right answer.
Okay.
There are many ways for a fluid to move and dissipate energy while still satisfying these equations.
That's pretty mind-blowing. It really expands our understanding of the possible ways fluids can behave.
Yeah.
But are there any limitations to their findings?
There's one key limitation they highlight.
Okay.
Their current method doesn't guarantee decreasing energy for all possible initial conditions,
Okay.
particularly those that are very rough or irregular.
So it's like their method works beautifully for a wide range of scenarios, but there are still some extreme cases where it needs further refinement.
That's a good way to put it.
So where does this leave us?
Wow.
This telescoping approach feels groundbreaking, like a new tool in the fluid dynamics toolbox.
It is, and it opens up so many exciting avenues for future research.
Like what?
How do these dissipative solutions behave in different physical situations? Can we connect them to real-world observations of turbulence? Can this method be extended to handle even more general cases like those with rougher initial data?
Wow, so many questions. I can already feel the gears in my head turning. You've given us a lot to ponder. Who knew viscosity could be so rebellious? This is definitely a deep dive I'm going to be thinking about for a while.
Me too.
Thanks for joining me today.
My pleasure. It's fascinating, isn't it?
It is.
To see how something we often take for granted, like the viscosity of a fluid, can unlock such profound mathematical insights and challenge our understanding of how the universe works.
It really highlights the beauty of scientific inquiry.
That constant pursuit of knowledge and the thrill of discovering something unexpected along the way.
Absolutely.
Speaking of mathematical techniques,
Right.
let's dive into the details of how they actually implemented this telescoping convex integration scheme.
Okay.
They start by describing the problem they're trying to solve,
Right.
finding solutions to the 3D Navier-Stokes and MHD equations.
Right.
And to be clear, we're talking about equations that describe the velocity and pressure of a fluid,
Yes.
as well as the magnetic field in the case of MHD.
That's right. And remember, these equations involve derivatives,
Okay.
which describe how these quantities change in space and time. Finding solutions means finding functions that satisfy these equations,
Okay.
meaning they balance out perfectly when you plug them in.
Right. It's like solving a complex puzzle where all the pieces have to fit just right.
Yes.
Now, this paper introduces a specific type of solution,
Okay.
a dissipative solution.
Right.
Can you unpack that a bit more? A dissipative solution is a special kind of solution where the energy of the fluid decreases over time.
Okay.
This is expected physically because viscosity, that internal friction within a fluid, causes energy to be lost as heat.
So it's like if you stir a pot of water, the initial energy from your stirring gradually dissipates and the water eventually becomes still.
Exactly. And the key contribution of this paper is proving mathematically that these dissipative solutions exist
Okay.
and can be constructed for both the Navier-Stokes and MHD equations.
Got it. Now they go on to describe their approach,
Okay.
which involves solving a sequence of simpler equations called the relaxed MHD Reynolds system
Okay.
at each step of the process.
Yes, and these relaxed equations are easier to work with
Okay.
because they involve something called a Reynolds stress and a magnetic stress.
Okay.
Think of these stresses as mathematical placeholders for the complex interactions happening within the fluid due to turbulence and magnetic fields.
Okay, so it's like they're temporarily simplifying the problem by representing those complex interactions as these stress terms.
Precisely. Now, their method, called telescoping convex integration, starts by finding a smooth solution to this relaxed system.
Got it. So they begin with a nice, well-behaved solution as their starting point.
Exactly, but this initial solution isn't perfect.
Right.
It doesn't perfectly capture all the intricacies of the real fluid flow. That's where the iterative process comes in.
Right. They need to refine their solution to get closer to the real deal.
Exactly. And they do this by adding carefully designed perturbations to both the velocity and the magnetic field at each step.
So it's like adding small ripples or disturbances to the smooth flow to capture more of the complexity of the real fluid behavior.
That's a good way to visualize it. Now, these perturbations are very specific.
Yep.
They're built using a technique called intermittent building blocks.
Okay.
Imagine these building blocks as localized, concentrated bursts of flow that are strategically placed within the fluid.
So they're not just random disturbances. They're carefully crafted and positioned to achieve a specific effect.
Exactly. And the key is that these perturbations are designed to interact with each other in a way that cancels out the errors introduced by the stress terms,
Okay.
gradually improving the accuracy of the solution with each step.
Ah, so it's like a delicate balancing act. They're adding these disturbances to make the solution more realistic, but they also need to ensure those disturbances don't create more problems than they solve.
Precisely. It's a very intricate process, and the math involved gets pretty intense.
I bet. But the beauty of it is that it works.
Yes.
They rigorously prove that this process converges,
Yeah.
meaning that as you keep adding more and more of these carefully designed perturbations, your solution gets closer and closer to a true dissipative solution of the original Navier-Stokes or MHD equations.
That's right. Their results are a testament to the power of combining rigorous mathematical analysis with clever physical intuition.
And what makes this even more remarkable is that they achieve this for both the Navier-Stokes and the more complex MHD equations.
Indeed, the MHD equations bring in magnetic fields, which adds a whole new layer of complexity, but their method is robust enough to handle it.
I'm particularly intrigued by this concept of a heat corrector.
Okay.
It seems like an elegant way to manage the errors that inevitably arise in the process.
The heat corrector is based on the idea that heat naturally spreads out and dissipates. They use this principle to design a correction term that effectively cancels out some of the errors that accumulate during the iterative process.
So it's like they're leveraging the natural tendency of heat to diffuse as a way to smooth out the wrinkles in their solution.
Exactly. Now, there's a fascinating mathematical concept connected to this called a pullback attractor, which the paper mentions.
Okay.
The pullback attractor describes a stable state that solutions to certain equations like the heat equation tend to evolve towards over time.
So are they suggesting that the heat corrector is somehow guiding their solution towards this stable state, thus reducing errors?
That's a good way to think about it. It highlights how they've cleverly exploited the mathematical properties of the heat equation to help control the error in their approximation scheme.
It's like they found a way to harness the inherent stability of certain physical processes to improve the accuracy of their mathematical model.
Precisely. And this is a powerful idea. with potential applications in other areas of mathematical modeling and numerical simulations.
Okay, so their method is robust. It leverages the physics of heat dissipation.
Yeah.
And it's mathematically rigorous. That's a pretty impressive package.
Yes.
But you mentioned a key limitation earlier. Can you remind us what that is?
Of course, while their method is successful for a wide range of initial conditions, it doesn't guarantee decreasing energy for all possible initial data.
Oh.
They specifically point out that their current approach might not work for initial conditions that are very rough or irregular.
So it's like they've made a significant breakthrough, but there are still some frontier areas where more research is needed.
Exactly. Science is an ongoing journey, and this paper opens up exciting new paths for exploration.
Like what?
For example, can we extend this method to handle even more complex and irregular initial data?
Okay.
Can we find connections between these dissipative solutions and real-world observations of turbulence, which is notoriously difficult to model?
Right.
These are just a few of the intriguing questions this research raises.
It's like they've shown a light on a previously hidden landscape, revealing all sorts of fascinating features and prompting us to explore further. Now, in addition to the theoretical results, the paper delves into some specific examples to demonstrate their method in action.
Right.
Let's take a look at those.
Certainly, they first introduced something called the lambda MHD system, which, as we discussed earlier, is a way to approximate the MHD equations by focusing on the low-frequency modes of the fluid's motion and allowing the high-frequency ones to dissipate.
Right. It's like filtering out the high-pitched noise to concentrate on the more dominant lower frequency sounds.
Exactly. And this simplification makes it easier to find smooth solutions that serve as a starting point for their iterative process.
Got it. So what specific examples do they explore using this lambda MHD system?
One example involves starting with an initial velocity and magnetic field that are both smooth and have finite energy.
Okay.
Their goal is to construct dissipative solutions that evolve from this initial state.
Okay.
They use their telescoping convex integration scheme to do this iteratively, adding those carefully designed perturbations we discussed earlier.
So they're essentially showing how their method can be used to generate these dissipative solutions, starting from a well-defined initial state.
Exactly. And they prove rigorously that this process leads to solutions where the energy decreases over time as expected for a dissipative system.
That's a convincing demonstration of their method in action. Do they explore any other examples?
They do. Another interesting example involves exploring what happens when you start with initial data that's in a special mathematical space called H12.
Okay.
This space is important because it represents the borderline between smooth and rough initial conditions.
Ah, so it's like they're testing their method on a more challenging scenario where the initial data might not be as well behaved.
That's right. And what they find is fascinating. Even for this borderline case, they can still construct solutions that are continuous in time and have continuous energy profiles.
So even when the initial data is a bit rough around the edges, their method can still produce solutions that make sense physically.
Exactly. It speaks to the robustness of their approach now in delving into the details of their method. The paper introduces some intriguing mathematical tools and concepts.
Okay.
One that caught my eye is the use of geometric lemmas.
Oh, yes. These geometric lemmas are crucial for constructing those intermittent building blocks we discussed earlier.
Certainly imagine you're trying to build those localized bursts of flow, those box flows within the fluid.
Right.
You need a way to ensure that these bursts are concentrated in specific regions and don't overlap too much.
Right. It's like carefully placing puzzle pieces so they fit together without gaps or overlaps.
That's a good analogy, and that's where the geometric lemmas come in. These lemmas provide mathematical tools to create these localized building blocks in a very precise way.
So they're like blueprints for constructing those intermittent bursts of flow.
Exactly. And the beauty of these lemmas is that they guarantee certain geometric properties, like non-overlapping supports for different building blocks.
Ah, so they're like quality control checks, ensuring that the building blocks are constructed in a way that won't mess up the overall solution.
Precisely now, in the context of MHD, where you have both fluid flow and magnetic fields, these geometric lemmas become even more critical.
Okay.
Because you need to ensure that the building blocks for the velocity field and the magnetic field are compatible with each other.
Right. It's like coordinating the movements of two dancers to create a harmonious performance.
I like that analogy. And these lemmas provide the mathematical framework to ensure that the velocity and magnetic field perturbations interact constructively and contribute to the overall convergence of the solution.
It's fascinating to see how these seemingly abstract mathematical tools play such a vital role in capturing the complexities of fluid dynamics.
It is, and this highlights the beauty of mathematics, its ability to provide a precise language and powerful tools to describe and understand the intricate workings of the natural world.
Now, in addition to the geometric lemmas, the paper introduces some advanced analytical techniques to estimate the size and behavior of those perturbations they're adding.
Right.
One concept that caught my attention is temporal intermittency.
Ah, yes. Temporal intermittency is a key idea that helps them control the growth of errors over time.
Can you break down what temporal intermittency means in this context and why it's so important?
Certainly remember those localized bursts of flow? We discussed those box flows.
Yes.
Temporal intermittency refers to the idea that these bursts are not only spatially localized, but also occur intermittently in time.
So it's not like these bursts are constantly present, they pop up and disappear at specific times.
Exactly, and this is a crucial feature for controlling errors.
Okay.
Imagine if those bursts were always present, they would constantly interact with each other and potentially lead to a buildup of errors over time.
Right, it's like having too many cooks in the kitchen, things could get chaotic.
Exactly. By introducing temporal intermittency, they ensure that those bursts of flow interact only for short periods, preventing a runaway accumulation of errors.
So it's like they're strategically scheduling those bursts to minimize their interactions and keep the errors under control.
That's a good way to visualize it. They use sophisticated mathematical techniques to carefully choose the timing and duration of those bursts, ensuring that the overall error remains small.
It's remarkable how they've combined spatial localization and temporal intermittency to achieve such fine-grained control over the solution's behavior.
It is, and this highlights the importance of considering both space and time when modeling complex systems like fluids.
Now, in analyzing those perturbations, they also use some powerful tools from harmonic analysis.
Right.
Can you give us a glimpse into how those tools come into play?
Certainly, harmonic analysis provides a way to decompose functions into different frequencies, just like you can break down a musical chord into its individual notes.
So it's like they're analyzing the frequency content of those perturbations to understand their behavior.
Exactly, and this is crucial for controlling how those perturbations interact and contribute to the overall solution.
Can you give us a specific example of how harmonic analysis helps them in this process?
Of course, one way they use harmonic analysis is to estimate the size of those perturbations in different function spaces.
Okay.
These function spaces, like LP spaces, provide a way to measure the smoothness or roughness of a function.
So it's like they're quantifying how well-behaved or wild those perturbations are.
Exactly, and by carefully controlling the size of the perturbations in these different function spaces, they can ensure that they don't disrupt the overall solution's behavior.
It's like ensuring that the individual dance moves, while expressive, don't throw off the overall choreography of the performance.
I like that analogy. Now, harmonic analysis also helps them analyze how those perturbations interact with each other. Remember, they want those interactions to cancel out errors.
Right, it's like those bursts of flow are engaged in a delicate dance to maintain balance.
Exactly, and by analyzing the frequency content of those interactions, they can ensure that the destructive interference outweighs the constructive interference, leading to a net reduction in errors.
It's like they're fine-tuning the frequencies of those interactions to achieve the desired error cancellation.
That's a good way to think about it. It's a testament to the power of harmonic analysis to provide insights into the intricate interplay of different components within a complex system.
Now, as we delve deeper into the mathematical framework, the paper introduces something called mollification.
Right?
Can you shed some light on what mollification is and why it's needed in this context?
Certainly, mollification is a mathematical technique used to smooth out functions.
Okay.
It's like taking a rough, jagged edge and sanding it down to make it smoother.
Okay, so it's a way to make those perturbations more well-behaved.
Exactly. Yeah. Now, you might wonder, why do they need to smooth out those perturbations?
Yeah.
Didn't we want them to introduce some roughness to capture the complexities of fluid flow?
That's a good point. It seems a bit counterintuitive.
It does, but there's a subtle reason behind it. While some roughness is needed, too much roughness can cause problems. Okay. It can lead to instabilities and make the mathematical analysis more challenging.
So it's like finding the right balance between introducing complexity and maintaining mathematical control.
Precisely, mollification helps them achieve that balance.
Okay.
By smoothing out the perturbations just enough, they can retain their essential features while making them more manageable from a mathematical perspective.
So it's like they're taming those wild bursts of flow without completely stifling their energy.
That's a great way to put it. Now, the specific way they implement mollification involves something called a convolution with a smooth function.
Okay.
It's like taking the original function and averaging it over a small neighborhood, effectively blurring out any sharp features.
So it's like applying a soft focus filter to a photograph, reducing the harshness of any sharp edges.
That's a good analogy, and the choice of that smooth function called the mollifier determines the degree of smoothing.
So they can fine-tune the level of smoothing based on the specific needs of the problem.
Exactly. It's a versatile technique that allows them to introduce just the right amount of smoothness to make the mathematical analysis tractable without losing the essential characteristics of those perturbations.
It's remarkable how they've combined sophisticated mathematical tools like geometric lemmas, harmonic analysis, and mollification to construct these dissipative solutions.
It is, and this highlights the power of interdisciplinary thinking, bringing together concepts from geometry, analysis, and physics to tackle challenging problems in fluid dynamics.
Now, in their concluding remarks, the paper outlines some potential avenues for future research. Can you summarize some of those exciting directions?
Certainly one promising direction is to explore whether their method can be extended to handle even more general cases.
Okay.
Particularly those involving rougher initial data. Remember, their current approach has limitations when dealing with highly irregular initial conditions.
Right. It's like their current toolbox is well equipped for many scenarios, but might need some additional tools to tackle those extreme cases.
That's a good analogy. Another fascinating avenue is to investigate the connection between these dissipative solutions and real-world observations of turbulence.
Okay.
Turbulence, with its chaotic and unpredictable nature, has long been a challenge for fluid dynamicists.
So the question is, can these dissipative solutions provide new insights into the behavior of turbulent flows?
Exactly. It's an open question that holds the potential to bridge the gap between theoretical models and experimental observations.
That would be a significant step forward in our understanding of turbulence. Are there any other research directions they highlight?
They also suggest exploring the behavior of these dissipative solutions in different physical settings, such as in the presence of boundaries or external forces.
So it's like taking their theoretical framework and seeing how it performs in more realistic and complex scenarios.
That's right. It's about pushing the boundaries of their model and testing its limits.
It's exciting to think about the potential discoveries that lie ahead as researchers continue to explore these avenues.
It is, and this paper serves as a testament to the power of human ingenuity to develop new mathematical tools and techniques to unravel the mysteries of the natural world.
Well, I think we've thoroughly unpacked this paper and extracted some truly fascinating insights. It's incredible to see how new mathematical tools and creative thinking can lead to profound advancements in our understanding of fluid dynamics.
It is, and this paper is a testament to the power of human curiosity and the relentless pursuit of knowledge. Who knows what other mysteries of the universe will unravel with the next wave of mathematical innovation?
That's a thought-provoking question to end on. It leaves us with a sense of wonder and anticipation for what the future holds in the ever-evolving field of fluid dynamics. Thanks for joining me today.
My pleasure.
All right, ready to dive into some really fascinating math today.
Absolutely. Always up for a good mathematical challenge.
Me too, especially when it involves concepts like dissipative solutions in the context of 3D Navier-Stokes and those magnetohydrodynamic equations, the MHD equation.
Oh, yeah. Those are some really intriguing areas.
They are. And I think our listeners, being the math experts they are, will appreciate the nuances we're going to uncover here.
For sure. This stuff gets pretty intricate.
It does. So we're going to be looking at excerpts from a research paper. The title is a mouthful. It's called Global Dissipative Solutions of the 3D Navier-Stokes and MHD equations.
Okay, sounds like a dense one. Lots to unpack there.
It is, and we're not just going to scratch the surface. We really want to understand not only what these solutions are, but also why they're so important in the field.
Right, because the why is often where the real excitement lies.
Exactly. Plus, we'll delve into some of the really ingenious techniques these researchers are using to study them.
Like what? Give me a teaser.
Well, one of the things that makes this research so compelling is that it tackles a very fundamental problem in fluid dynamics. How to prove rigorously that energy consistently decreases over time, especially in those complex 3D flows.
Yeah, that's a tough one. I mean, we observe this energy dissipation all the time in nature, right?
Exactly. Think about how turbulence in a river eventually calms down. It's everywhere.
Or how, like, a plume of smoke dissipates in the air.
Exactly. Capturing that mathematically, though, oh boy, that's a whole other challenge, wouldn't you say?
Yeah, it really is. And that's precisely where this concept of dissipative solutions comes in.
Okay, so these solutions are specifically designed to exhibit this energy decay property, but in a way that we can actually prove mathematically.
That's the goal. It's about building a rigorous framework to describe something we observe all the time. To really appreciate why this is such a big deal, though, we need to kind of look back at what we've already got, the existing types of solutions for these equations.
So kind of the landscape of solutions before this new research came along.
Exactly. And a key player in that landscape is something called Lorey-Hoff solutions.
Okay, I'm familiar with those, at least to some extent. They're a type of weak solution, right?
Yes. Weak solutions to the 3D Navier-Stokes equations, to be precise. But here's the catch. They don't always guarantee that the energy of the fluid decreases over time.
Really? They don't. I guess I didn't fully grasp that.
It's a bit subtle. They might exist for a whole bunch of different initial conditions, but there's this troublesome exceptional set of initial times, and at those times, the energy might actually increase.
Which seems counterintuitive, right? Like physically, we don't really see that happen.
Exactly. It's like a little glitch in the matrix. So this paper we're looking at, they're aiming to construct these dissipative solutions that basically overcome this limitation. They want solutions where the energy is demonstrably continuous, decreasing over time, and without those weird exceptions.
So it's like they're trying to refine our mathematical toolkit to better reflect the actual physical reality that we observe.
That's a great way to put it.
Now, before we get into the specifics of how they do that, their methods, and all the clever math involved, can we maybe take a step back and revisit the Navier-Stokes equations themselves for a moment? I'm sure our listeners are familiar with them, but even experts can appreciate a quick refresher, right?
Of course. Always good to ground ourselves in the fundamentals.
Right. So, at their core, what are the Navier-Stokes equations really telling us?
Okay, well, in essence, they're describing the balance of forces that act on a tiny little piece of fluid, a fluid element as it's moving.
Okay, a fluid element. So like, imagine a little, I don't know, a little cube of water within a larger flow.
Exactly. And there are different forces acting on that little cube. You've got pressure forces pushing on it from all sides.
Okay, pressure. That makes sense. What else?
Then you've got viscous forces. Those come from the internal friction within the fluid itself. It's kind of like the fluid's resistance to flow.
Viscous forces, so like the thicker the fluid, the stronger those forces would be.
Exactly. Like honey versus water, for example. Honey is much more viscous. And of course, you've got inertial forces, which basically represent the fluid's resistance to changes in motion. Like if it's moving in a certain direction, it wants to keep moving in that direction.
Right. Inertia objects in motion tend to stay in motion.
That's the idea. So the Navier-Stokes equations basically bring all of these forces together into a single mathematical framework.
They capture how those forces interplay as the fluid moves and changes over time.
Precisely.
But here's the thing, and I think this is where the real challenge comes in. Finding exact, or what mathematicians call strong solutions to these equations is often impossible, especially for complex flows in 3 dimensions.
Yeah, that's the big hurdle. It's like trying to solve a ridiculously complicated puzzle with pieces that keep changing shape.
And that's why mathematicians often focus on these weak solutions instead, right?
Right. It's a way to still analyze the equations even when we can't get those perfect, smooth solution that we might ideally want.
So it's a trade-off. We might lose some of the fine details, but we gain the ability to study the behavior of fluids in a broader range of situations.
Exactly. And in many cases, those broader insights are what we're really after.
Now, the paper also mentions the MHD equations. And I know that those bring magnetic fields into the mix. Can you tell us a little bit about that? How do they differ from the standard Navier-Stokes?
Sure. So the MHD equations, they specifically model fluids that are electrically conductive.
Electrically conductive. So not just your everyday water then.
Right. Think more like plasmas, the stuff that makes up stars, or certain liquid metals.
Okay, so pretty exotic stuff.
You could say that. And the key difference is that in these fluids, the magnetic field and the fluid motion are coupled. They actually influence each other.
Oh, wow. So the magnetic field affects how the fluid moves, and the movement of the fluid affects the magnetic field.
Exactly. It's like a two-way street, and that makes the equations even more complex, of course.
I bet. But it's also kind of amazing to think that the same basic mathematical framework can describe something as small scale as, say, a liquid metal experiment in a lab.
And something as vast as the dynamics of a star, yeah.
Exactly. It really speaks to the power of these equations.
It does. And what's so cool about this paper is that the techniques they're developing, they're actually applicable to both the Navier-Stokes and MHD equations, which really highlights their broad utility.
Now, I have to ask about this term MHD. What exactly does that refer to, and why is it important in this whole scheme of things?
MHD. It's a very clever tool. Think of it as a carefully crafted approximation of those full MHD equations.
An approximation, so it's like a simplified version.
In a way, yes. It's like applying a filter that smooths out some of the really fine-scale details of the fluid motion. Those tiny, chaotic eddies that are super hard to model directly.
Okay, so they're focusing on the bigger picture, so to speak.
Exactly. The larger scale patterns, the lower frequency behavior. And the beauty of it is that this MHD approximation, it can be rewritten into what's called a relaxed system, which really helps make those difficult to control components more manageable. They get bundled into things called Reynolds and magnetic stresses.
Okay, so it's a way to simplify the problem without losing sight of the essential physics they're trying to capture.
Exactly, that's the key. And this simplification, it sets the stage for their main solution method, which they call, are you ready for this? Telescoping convex integration.
Telescoping convex integration. That's quite a name, especially that telescoping part. What does that even mean in this context?
It's a very visual name for a very powerful technique. So imagine you're trying to create, I don't know, a sculpture, right? And you start with a rough block of material.
Okay, like a block of marble, maybe.
Perfect. And then you start chiseling away at it bit by bit, making small adjustments, adding details, until you eventually arrive at the desired form.
So it's an iterative process. You're refining it step by step.
Exactly. And that's the essence of convex integration. You start with an approximate solution, and then you iteratively add these carefully designed perturbations to it.
Perturbations, so like little nudges in a certain direction.
Yeah, you could think of it that way. And with each nudge, you get closer and closer to the true solution that you're after. Now, the telescoping aspect, that's where things get really clever.
Okay, I'm all ears.
They construct a sequence of energy levels for these perturbations. And these levels, they decrease in a very controlled way, kind of like a collapsing telescope where each section fits neatly into the next.
So it's like they're building a solution with this built-in energy cascade where the energy decreases at each step.
Precisely. And that's what ultimately ensures that the final solution will also have this decreasing energy property, which, remember, is the hallmark of those dissipative solutions we're after.
Okay, I'm starting to see how all these pieces fit together now. They simplify the equations with this MHD approximation. Then they use this telescoping convex integration to build a solution step by step, with decreasing energy at each stage. But how do they make sure that the energy actually decreases at each step? It seems like a pretty delicate balancing act.
It is. They have to be very careful about how quickly the energy of those perturbations grows. They have to make sure it doesn't outpace the natural energy decay that's already built into that MHD system.
So they're working with the natural tendencies of the system, but also carefully guiding it towards the desired outcome.
Exactly. And to make sure that happens, they employ a really neat strategy involving what they call backward and forward time sequences. They're denoted as TQ and SKU in the paper.
TQ and SKU, okay.
Yeah, it gets a bit technical, but the basic idea is that they divide the time interval into these segments, and then they work in both directions. In the backward sequence, they refine the solution near the initial time point, working their way back in time, so to speak.
I see, sort of like building a bridge from one end.
Exactly. And then in the forward sequence, they extend the solution forward in time, all while carefully maintaining that decreasing energy property, like building the bridge from the other end.
And making sure those two ends meet perfectly in the middle.
Precisely. And this careful back and forth construction, it gives them really fine-grained control over the energy profile of the solution. But, as you can imagine, with a scheme this complex, there's always the potential for errors to creep in.
That's what I was thinking. All those perturbations, all those delicate adjustments, it seems like there'd be plenty of room for things to go awry. How do they account for that? How do they make sure those errors don't just accumulate and derail the whole process?
That's where another layer of ingenuity comes in, something called heat correctors, which are super fascinating, but I think we'll save that discussion for part 2 of our deep dive.
A cliffhanger. Okay, I like it. We'll let our listeners stew on that for a bit. And when we return, we'll delve into the world of these heat correctors and all the mathematical magic they bring to the table. Okay, so heat correctors, right. Where do they fit into all of this?
They're really the key to keeping this whole intricate construction from falling apart.
So damage control, basically. Making sure those little errors that pop up along the way don't cause too much trouble.
Exactly. Because remember, we're working with equations that are incredibly complex, full of nonlinear interactions. And when you're building a solution iteratively, like they are with this convex integration method, there's a lot of room for discrepancies to accumulate.
So it's like you need a mechanism to smooth things out as you go, kind of like a mathematical ironing board, if you will.
That's a great analogy, and that's essentially what these heat correctors do. They're specifically designed to target those types of errors that crop up because of those nonlinear interactions between different parts of the solution as it's being built step by step.
It sounds like a delicate balancing act. I mean, how do you even begin to approach error correction in a system that's already this intricate?
Well, believe it or not, the name heat corrector actually gives us a clue. Think about the heat equation for a second.
The heat equation, the one that describes how heat diffuses over time.
That's the one. You start with a region that's, let's say, high temperature, and then over time, that heat naturally spreads out, smoothing out the temperature differences until you reach a nice uniform state.
Okay, yeah. Like if you put a hot cup of coffee on a table, eventually it cools down and reaches room temperature.
Exactly. And the key insight here is that heat has this inherent smoothing property. And that's precisely what they're leveraging with these heat correctors. They're using this concept to essentially smooth out those errors that pop up in that convex integration scheme.
Oh, I see. It's like they're borrowing the smoothing power of heat to guide the solution towards a more stable form, kind of like ironing out those wrinkles as they go.
Exactly. It keeps those errors from spiraling out of control and potentially messing up the entire construction.
So to recap, we've got this MHD approximation that simplifies things, then the telescoping convex integration that builds the solution step by step, and along the way, these heat correctors are working behind the scenes to keep those errors in check. Did I get that right?
You got it. It's like a well-choreographed dance. And what's so impressive is that it's all grounded in a really deep understanding of not just the mathematical structure of the equations, but also the physical realities of fluid dynamics. They're not just manipulating symbols, they're developing a framework that actually reflects how fluids behave in the real world.
Which brings us back to turbulence, right? That wonderfully complex and ubiquitous phenomenon that we still struggle to fully understand.
Precisely. And while this research doesn't completely solve the puzzle of turbulence, it does represent a big step forward in terms of how we can model and predict its behavior. By proving the existence of these dissipative solutions, they're giving us a more mathematically sound and physically realistic framework to study how energy behaves in those turbulent flows.
And to think, it all comes down to these subtle yet powerful concepts, like heat correctors and those telescoping energy levels. It's really quite beautiful when you think about it. But even if they've successfully constructed these dissipative solutions, does that mean the case is closed? Is turbulence solved?
Not quite, because remember, they've demonstrated the existence of infinitely many of these dissipative solutions.
Oh, right. I forgot about that. So infinitely many solutions. What does that mean for us? Does it make things easier or harder?
It definitely raises some interesting questions. Because now the challenge becomes, how do we know which one of those infinitely many solutions will actually show up in a given physical situation? What are the rules, the selection principles that govern which solution wins out in a particular turbulent flow?
That's a great point.
Yeah.
Just because we have a bunch of valid solutions doesn't mean we understand how nature chooses which one to actually use in a given scenario. It's like having all the ingredients for a cake, but not knowing the recipe.
That's a perfect analogy. It opens up this whole new frontier in turbulence research. We're not just trying to prove that solutions exist anymore, but really understanding the dynamics of how those solutions evolve and potentially interact or even compete with each other within a turbulent flow.
So the next big challenge is to delve into those questions of stability and selection to figure out why certain turbulent structures emerge and persist while others fade away.
Exactly. What are the mathematical and physical mechanisms behind that selection process? That's where things get really interesting.
Okay, so we spent a lot of time in the weeds here, haven't we? Really digging into those theoretical nuts and bolts behind these dissipative solutions, all those MHD approximations and telescoping convex integration and heat correctors. It's been pretty intense.
It has, but the math is really elegant, isn't it?
Oh, absolutely. But I have to admit, my brain is starting to hurt a little bit. I'm really curious to explore the so what of all of this. What are the practical implications of this research? Like, how does this all actually translate to the real world?
It's a great question, and it's something that every mathematician, especially those working on, abstract theoretical problems, really grapples with.
Right. How do you bridge that gap between the beauty of the theory and the messiness of reality?
Exactly. It's one thing to prove that these dissipative solutions exist on paper, but what does that actually tell us about how fluids behave out there in the wild?
Yeah, like how do we take this abstract mathematical framework and extract tangible insights from it?
Well, I think the best place to start is by going back to turbulence. We've talked about how it's incredibly common, incredibly complex, and still, not fully understood.
Oh yeah, turbulence. It's everywhere, isn't it? Affecting everything from the weather to how efficient airplane wings are to how blood flows through our veins.
Exactly. And those Navier-Stokes equations, as powerful as they are, they're notoriously hard to solve in 3 dimensions,
Yeah.
especially when you throw turbulence into the mix.
It's like the equations themselves become turbulent.
Right, and that's precisely where these dissipative solutions come in. By proving that they exist, we're getting a much firmer mathematical foundation for understanding how energy behaves in those turbulent flows. Remember how we talked about those exceptional sets of initial times in the Luray-Hoff solutions, where the energy might actually increase?
Yeah, that always seemed kind of wonky to me.
Right, it didn't really make physical sense. Well, these dissipative solutions, they get rid of that problem. They give us a model that's much more consistent with what we actually see in nature, where the energy consistently decreases over time.
So it's about refining our mathematical tools to better reflect reality.
Exactly. And that has huge implications for how we simulate and predict turbulent flows. Imagine creating more accurate weather forecasts or designing airplanes that are way more efficient, all because we have a deeper understanding of how turbulence actually works.
Okay, now that's what I'm talking about. That's the payoff, right?
Yeah.
More accurate models lead to better predictions, better designs, better everything.
Absolutely. But, and this is a crucial point, even though these researchers have made some major breakthroughs in constructing these dissipative solutions, it doesn't mean we've solved turbulence. In fact, their findings actually raise some intriguing new questions.
Oh, really? Like what mysteries are still out there?
Well, remember that they proved the existence of infinitely many dissipative
Oh,
solutions.
right. I forgot about that part. Infinitely many solutions. So how do we deal with that? Do they make things easier or harder?
Well, it definitely adds another layer of complexity. Because now the question becomes, out of those infinitely many solutions, which one is actually going to show up in a given situation? What are the factors that determine which one wins out?
It's like having a million different keys, and only one of them actually unlocks the door, but you don't know which one.
That's a good way to put it. It really opens up a whole new frontier for turbulence research. It's not just about proving that solutions exist anymore, but about understanding the dynamics of how those solutions evolve, how they might interact with each other, and even how they might compete within a turbulent flow.
So the next big challenge is to dive into those questions of stability and selection, figuring out why certain patterns emerge from the chaos of turbulence while others just kind of fizzle out.
Exactly. What are the mathematical and physical mechanisms that drive that selection process? Those are the big questions now.
Wow, so much more to explore. It seems like with every answer we find, we uncover even more questions.
That's the beauty of science, isn't it?
It is. And honestly, it's what makes this whole journey so exciting. There's always more to learn, more to discover. I mean, this paper, it's a major stepping stone. It gives us amazing new tools to really probe the depths of turbulence, but it also reminds us just how much we still don't know.
And it's that not knowing, that curiosity that keeps pushing us forward.
Absolutely. I think it's safe to say this deep dive has given us, and hopefully our listeners, a much deeper appreciation for both the elegance and the practical power of math. It's really shown us how even the most abstract concepts can have a real impact on our understanding of the world.
I couldn't agree more. It's been a real pleasure exploring these ideas with you.
Likewise. And to all our listeners out there, thanks for joining us on this deep dive into the fascinating world of dissipative solutions and the never-ending quest to understand turbulence. We'll see you on the next one.